Welcome back. We're going to look at the ammonia problem. I chose it because I'm trying to do a whole lot of things in the one, just as a run through. But remember, the ammonia one is an equation, very popular, and it's one that we use a lot because it's a big industrial process, the manufacture of ammonia through the Haber process. So the first question, they say, write a balanced chemical reaction for ammonia. Okay, well, that we know is, how do we make ammonia? We put, and that's got to go to there, we're going to put nitrogen gas plus hydrogen gas, and that goes to, I'll put the arrows both ways particularly, that goes to NH3 ammonium, as opposed to ammonia, which is the positive ion, remember? That's going to come later on. So let's have a look, let's balance it. First of all, we balance the metals, non-metals, then the remainder, the hydrogens and the oxygens. So we need 2 N's over there, and now we've got 6 hydrogens, so we need a 3 there, correct? So that's how we're going to write the balanced chemical reaction. The next question is, they ask, using a table of values given, is it endo or exothermic? Okay. Now remember, exo means exit. It's go out. The heat is out. So exo and exit mean the same thing, right? So if we've got an exothermal reaction, exothermic, it means that heat is given off, right? Let's just have a look. What does the graph of these things look like? And we'll just get down to some of them. Let's have a look here. We've got over here, up there, exaggerated. This is my reactant over here. So this is our N2 and H2 on this side. This is our product. Okay. Now, we know that it could go both ways. It could also, we will add the heat in, and it could come down over there like that, right? So that gives us an exo versus an endo thermic reaction, where the exo has given off heat. What do we mean at this point here? Quite simple. We mean at that point over there. Let's just have a look what we've got, okay? I'm just going to take two of these guys over here. Okay? These characters, okay, they're nice and bright. What have I got? I have got here a nitrogen and a hydrogen, okay? Can you see there's my N2 stuck together, and here's our H2 stuck together, right? Now, we know that they are going to be quite comfortable with each other to sit together as N2 and H2 because they're diatomic gases, okay? And there's no polarity on those. If you remember, they are quite simply just going to be happily sitting together. Now, in order for us to take that, we have to take nitrogen and we have to break the nitrogen apart, like so. Otherwise, we're not going to get anything. It's just going to stay together, right? Now, we know that nitrogen, if you remember back, nitrogen has got a triple bond with another nitrogen. Where does that come from? Just to recap, what did we have here? We had a nitrogen. Let's have a look. Nitrogen, remember, you look at its valency, you look and you see it's 1, 2, 3, 4, 5, 6, it's number 7. So nitrogen is a 7. Therefore, 7 electrons, 7 protons, 1 S2, 2 S2, that's 4, and 2 P3. So what have we got? On the outside, those are our valence electrons. We've got 5. So I'm going to go 1, 2, 3, 4, and I'm just going to put him here. Then we had our other nitrogen coming along over there. 1 there, 1 there, 2 there, and 1 there. And what happens? These guys get together, they bond, they bond, they bond. There's your triple bond coming from the nitrogen bonding together. So there's our 2 nitrogens sitting together like that. Okay? Now what do we have to do? Well, let's just complete the table. We've got the hydrogens. We know that we had the hydrogen was like this, correct? The H has got a 1, and this H had that, and those two get together and bond with one electron to form H2. Here this gives us our N2, and that gives us an H2, right? Now, let's just go back and look at this curve here, because what we are saying is that at this point here, we have to add energy, which is called activation energy. In other words, we have to get this reaction to occur. Okay? And now, let's just get that. Okay? We've got to get our reaction to occur. Okay. So, what is the next part of the process, right? Well, the next part of the process is we've got to take these apart, right? So we've got the nitrogen, we've got to pull them apart. We have to break the 3 bonds, right, between them. We have to pull those electrons out, don't we? Similarly, we have to take the hydrogens and we have to pull them apart. That is what we do, is when we add the activation energy, we input heat, right? So we put heat in over there. Let's just label it as red, okay? We put heat in because you know that what happens is the activation energy, correct? Okay, increases the velocity of the molecules. Because why? Because temperature is a measure of velocity, because it measures EK, which is equal to a half mv squared. Correct? That's what's actually happening over there. Okay. Now, we've got that measurement over there of the temperature proportional to the velocity. So now, if we heat it up, we break apart these 2 molecules of nitrogen and hydrogen. Well, because we're going to make NH3. Okay. So let's just have a look. I like to look at it and say, this side here is the breakup. This side is the makeup. Okay? Why? Because we are making product. We are synthesizing, which is the manufacture. Okay? As opposed to decomposing, which is the breakdown. That can also happen. The ammonia can break down back to the nitrogen and the hydrogen if we like. So let's have a look here and say, all right, let's look at the breakup side of this equation, shall we? First of all, now if you look, what have we got to do? We've got to break up that, right? But we've got to break up 3 of these guys, haven't we? Okay. We've got to break up 3 of those guys, like that. Okay? Because those 3 are the 3 hydrogens. Remember, to balance all this out, we needed to have 3 of these hydrogens, right? Because 2 are going to split off and go there. We've got to break another one and another one to get enough to bond to make 2 nitrogens. Correct? Okay. So let's take this a step further then. Okay. How much energy? Now, if you look at the table, you will see that the energy, bond energy, is given in kilojoules per mole. Okay? Which means it's the energy to break apart all of those 3 bonds in 1 mole of nitrogen gas. So what do I have to do? I have to break those apart. So I need to break, that is, and if you look, you'll see an N triple bond N, that is 946 kilojoules per mole. Now let's have a look. To break a hydrogen bond, okay, is 436 kilojoules per mole. But hold on, we've got to break apart 3 of them, haven't we? So it's going to be plus 3 times 436. And the total comes out there. Let's get it back to the black. Total comes out as 2254 kilojoules per mole. Okay, so where are we now? This is the energy added, right? Okay, so where are we then? Well, quite simply, we are We are on our curve. We are now, let's just draw our curve in here. We were there. We've now gone. That is what we've put in. Okay? 2254. So we've raised it from there to there. Okay? Now, let's have a look at the opposite side, shall we? Okay? Let's have a look at the breakup side. Or rather the makeup side. Right? We're making up in like that, aren't we? So if you look at each individual one over here, each of the atoms of ammonia are composed of, let me just get another one of those out there. Okay, there we go. There we go. Can you see there? That's what we've got, isn't it? Can you see it? We've got, I know this one's orange, forgive me for that, but what we've got there is we've got 3 NH bonds. So we've got to break that one, and that one now, right? So NH3 looks like that. I know we've got other electrons and so forth, just from a visual point of view. We've got to break this, or make this, make that, and make that, haven't we? That's what we're essentially trying to do now, right? In this process. Okay? So if you look on the table, you'll see the energy for one of those NH bonds over there is 390. Okay? But we've got 3 of them times 3. Okay? But hang on, we've got 2, remember? We're making up, from our balanced equation, we're making up 2 of them. We had the 3 hydrogens that we broke. We're making 2 of those. So we've got to account for that in the maths of this. Okay? And what we're going to do is we're going to say, okay, it's going to be times 2. So the total energy we get here is 2340 kilojoules per mole. Okay, where are we now then? Quite straightforward. Let's go back to black. We've gone up 2254 and we've gone down 2340. Right? So we know there. So you can see that if you take the 2 apart, it's 86. Okay? Okay? There. Delta H is equal to 86 kilojoules per mole. Right? So in this situation, we always go back to this, right? Remember, we say that the energy is equal to, or change in energy, is going to be E final minus E initial, right? E final minus E initial, okay? Can you see here that on an exothermic, okay, this is the E final, this is the E initial. E final, E initial, right? Okay, is going to give us, we're going to lose energy. Final is bigger than the initial state. Okay? So what are we going to get? We're going to get that we've gone down, haven't we? We've lost energy. Okay? So there's a net loss of heat in the exothermic. Okay? Now, the other side, there we've got the loss. Okay? Delta H over there. All right? On the endothermic, you've got, let me just draw it again. On the endothermic side, we've got a situation where we had here, okay, and in this case, all right, we've got E final, E initial. E final is bigger, so we get delta H is positive, okay? Let's just go back down on this one. Delta H is going to be negative here, isn't it? Okay. For example, EF could be 2,000. EI, it was higher. It's 3,000, right? So delta was minus 1,000. Can you see how it has dropped down? And over here, delta E is going to be equal to EF minus E initial. EF in this case was higher. So delta is going to be positive, right? Now, whenever you look at these over here, right, the best way, or the way I think of it, is the energy is stored in the bonds, right? So what we've got is we've got those three nitrogen, or those nitrogens that were stuck like that, okay? You know it's got a 3 bond. So we've got to think of each one like an elastic band, because that's what's the energy is being held in place by that elastic band. So we've got these guys, and we've got 3 elastic bands joining them. That's the bond energy between these guys, right? So in essence, in any of these calculations, what do? We first of all, we look at our reactant side. What is reacting with what? Let's just go back up to the graph where we started. We said, all right. We go back and we've got the breakup and the makeup, all right? You can see it there. What are we doing here? We're saying this, okay? We start on this side. This is our reactants, and this is where we're going to do the makeup on that side. We're going to add energy to get to what we call the activation complex over there, right? The activation complex is in essence when all we've done is we've separated everybody. So now, what do we have if we go back to my colorful props over here? We had that, we've split it apart. Now we've got these two can now go and react with something else, can't they? As they were here, they're not going to react with anything. They're going to just stay. We tear them apart. They can now react. They are in my activated complex. I have activated it. In other words, started the process. Here we go now. Those are apart. Now, these can go and, depending upon the circumstances, they can go and join with each other, can't they? That's what we're talking about with this activated complex. And what is this EA, the activation energy? It's the amount of energy that we need to tear these apart. At this stage, that's heat. We add heat into it. That's what's ripping these guys apart over here. All right? Of course, there's other ways of doing it as well, but for our purposes, heat. So now in the complex, we've got these guys floating around. Now they can go ahead and go and join. So then we can say whether it's endo or exothermic. Remember that an endothermic reaction, what has actually happened, let's just, I'm not going to take a specific example, but let's just think about an endothermic reaction just very quickly. What has actually happened is, this is the product, isn't it? Up here. This is the reactants down here. Okay. What have we got? We've got a situation here where the product has got more energy stored in it than originally the reactants had. So what we've done is we've bonded them, and there's more energy stored in those internal bonds of those, in the internal bonds of those molecules. Okay. Thanks for watching that one. As I say, you know, I hope it's sort of, we're going at the right pace with these. I'm going to get feedback, no doubt, from people. But really, you know, think about how much of this, just from the basics, is actually an exceptionally logical science, okay? Chemistry builds on different levels. As I've always said, physics is different suburbs, different houses in different suburbs. So it's a different topics all on their own. They do all come together. The beauty is when chemistry and physics join, which happens later on in towards the end of grade 12, we'll see how all of this stuff all joins together. Okay. Thanks for watching. Have a great prep for the exams. And like I say, please make sure you learn all the theory side, the laws, etc., etc. Cheers.